Howdy folks, welcome to Calculus again, and what we're going to talk about in this video is implicit differentiation. Now, implicit differentiation is a special general form of a derivative, and it's something that you need to understand, especially if you're going to go into higher levels of mathematics or into applied areas of mathematics. Implicit differentiation allows you to take a derivative of an equation that includes multiple variables. See, what we've done up to this point is you have only done the derivative of functions where we have y is equal to, let's say, 7x to the 5th power minus 2 to the x power plus log base 4 of x is equal, or it's not equal to, sorry, minus 16, okay? I mean, it can have some trig functions in there and stuff, but in every case, all of your functions had included just the letter x, or just one variable, okay? And then you have y on this side, y equals. Implicit differentiation allows you to find a derivative that includes multiple variables. For example, what if you were dealing with the area of a triangle, which is area is equal to 1/2 base times height. We have three variables here. We have area, base, and height. And what if that triangle was changing over time? Well, that would include time now, and you'd have a total of 4 variables. So, implicit differentiation is a very flexible derivative technique that allows you to take the derivative of pretty much anything. Okay? So, we're going to learn how to do that. In this particular case, you'll see that this is a complicated relation here. It has x to the 3rd power, it has minus 2y to the 5th power, it has a 4y over here and a minus 6x squared. So it has two variables, but both variables have coefficients and powers and that sort of thing. It's not just y equals a bunch of x stuff, okay? So we want to identify the derivative dy dx. dy dx is the instantaneous change in y when there's an instantaneous change in x. So how much is y changing when x changes at just one moment, at an instant? Okay? So the very first step, the first thing you're going to do is apply the appropriate derivative rule to each term. And there's one more thing. While you're doing this, here's the special part. Put a dy dx on all y terms. So every time you do the derivative of something that has y instead of x, you're just going to put on a dy dx. Let me show you what I mean. What's the derivative of x to the 3rd power? It's 3x squared. 3x squared. But because it's an x term, we are not going to put a dy dx on it. Now let's do the derivative of negative 2y to the 5th. Well, the derivative of negative 2y to the 5th is we got to do the 5 times the negative 2, that's negative 10, y, and then reduce the power by 1, so it's y to the 4th, right? So we've got 3x squared minus 10y to the 4th power. Now, because we just did the derivative of a term that had y in it instead of x, we're going to put on a dy dx, and it's being put on through multiplication. So it's going to be 10y to the 4th times dy dx. What is that, Mr. Ryan? What is that dy dx? It's basically a conversion factor. It's a conversion factor because this is giving us the rate of change in y instead of the rate of change in x. Since we're doing the derivative of a function with respect to x, we need to convert our y term into x term using this conversion factor. So we just slap on a dy dx equals. Okay, now we did the left side. Now let's do the right side. what is the derivative of 4y? Well, if this was 4x, wouldn't the derivative just be 4, right? So it's the same thing with 4y. The derivative of 4y is just 4, okay? But because we did the derivative of a y term, what do we have to put on? We got to put on a dy dx. So it's 4 dy dx. And what you need to do is, what you should do is start viewing dy dx, this thing, as its own variable. It's one whole thing. It is a variable. Now, then we got minus 6x squared. The derivative of that is minus 12x. Minus 12x. And so this is the derivative of this. But we're not done, because the question said to solve for dy dx. See, we need to isolate the dy dx. We need the dy dx to be by itself. We need something that says dy dx equals, and everything else on the other side. So we got to do a little bit of algebra here. So the next step, step 2, is move all terms with dy dx to the left side of the equals, to the left side of the equal sign. So we're going to move this 4 dy dx over to this side. How? Well, it's a positive 4 dy dx, so we're going to go minus 4 dy dx, and that's going to cancel it. But if I minus 4 dy dx on this side, I have to minus 4 dy dx on this side, because it's an equation. It has to remain balanced. Now, the next thing you're going to do, step 3, is move all terms without dy dx, to the right side. To the right side of the equation, right side of the equal sign. So this term has a dy dx, and this term has a dy dx, but this term, this 3x squared, does not have a dy dx on it. So we're going to subtract 3x squared here. That's going to cancel this. And we're going to subtract 3x squared on the right side. And now we just have to clean it up. So over here, all we have left is this and this. And over on this side, we have this and we have this. So we're going to have negative 10 y to the 4th dy dx minus 4 dy dx equals, let's do negative 3x squared minus 12x. And so now we've moved all our dy dx terms to the left and all our non-dy dx terms over to the right. 2 more steps. Step 4. Now, only on the left side, what we want to do is we want to factor out a dy dx. See how both of these terms are multiplied by dy dx? That means that it's a greatest common factor. We can factor out the dy dx and put it on the outside of a set of parentheses, and on the inside of the set of parentheses will be just the negative 10y to the 4th and just the minus 4. So we're going to factor out the dy dx. And what we're going to have is dy dx times negative 10y to the 4th minus 4. We have undistributed. That's what factoring is. It's undistributing. We have undistributed dy dx. Now, if we were to distribute the dy dx, we would multiply it to this, and we'd multiply it to this, and we would have what we had in the previous step. Okay? All right, so we've got dy dx times negative 10y to the 4th minus 4. The right side we didn't have to change at all. We just still have negative 3x squared minus 12x. So step 4 is factor out dy dx from the left side, of the equation. Okay? Last step, step 5. Use division to isolate dy dx, which basically means we're going to divide on both sides. We're going to divide on both sides by what's being multiplied by dy dx. So if we divide by negative 10 y to the fourth minus 4, if we divide by that on both sides, negative 10 y to the fourth minus 4, we're dividing by it on both sides, so it's algebraically consistent, it's legal. On this side, it's going to cancel, and all we're going to have left is dy dx. So, divide on both sides to cancel what is with dy dx on the left. So we're just canceling whatever's with the dy dx on the left so that dy dx can be by itself. And so our answer now is going to be dy dx. Let's just rewrite it. Our final answer is dy dx is equal to negative 3x squared minus 12x over negative 10y to the fourth minus 4. There we go. And that's our derivative. Now, something that may interest you, I don't know if you noticed this, is our derivative has an x and a y in it, or two x's and two y's. What this means is that in order for you to be able to identify the rate of change in the relation, in order for you to identify the slope of the relation at a point, you need more than just an x value. You will need an x value and a y value to plug both in. You'd have to plug an x here and here and a y in right here in order to get the derivative. Okay. And you can't just pick any x value and any y value. It has to be an x value and a y value that work, that fit, that are consistent in the original relation that you were working with. Okay, let's do a couple more examples. Okay, so we've got this implicit equation here. Includes x squares and y squares, and we want to find dy dx. You may want to pause this and try this procedure on your own, or you can just follow along with me. So step 1 says apply the appropriate derivative rule to each term. The derivative of x squared is 2x plus the derivative of y squared is 2y, but because it's a y term, we're going to put a dy dx on it. So dy dx. Now, the derivative of the constant 9 is 0, so we're just going to leave that out. That goes away. Equals, the derivative of 6x is 6. The derivative of 4y is 4, but because it's a y term, we're going to put a dy dx on it. There we go. That's now we're going to go to step 2. Move all terms with a dy dx over to the left side. Well, this one's already on the left, so we just got to go minus 4 dy dx on this side and minus 4 dy dx on this side. Okay? Step 3, move all terms without a dy dx to the right side. Well, this one's already on the right side. This one over here doesn't have a dy dx, so we're going to subtract 2x here, and we're going to subtract 2x here. And so now on the left side here, we have 2y dy dx minus 4 dy dx. So 2y dy dx minus 4 dy dx equals 6. Over here we have 6 and we have minus 2x. 6 minus 2x. Okay, that's up to step 3. Step 4, factor out dy dx from the left side. So over here on the left side, we're going to factor out the dy dx's. We're going to move them to the outside, and then we're going to put parentheses around the 2y minus 4. Okay? So we're going to have dy dx on the outside, parenthesis 2y minus 4 is equal to, this side stays the same, 6 minus 2x. Last step, divide on both sides to cancel what is with the dy dx. Well, what's with the dy dx? This thing is the 2y minus 4. So we're going to divide by 2y minus 4 here, and we're going to divide by 2y minus 4 here. That, on this side, it's going to cancel, and all we have left is dy dx. So that gives us our answer. Our rate of change dy dx is equal to 6 minus 2x over 2y minus 4. 2y minus 4. Now you may notice that you can actually factor out a 2 from the numerator and from the denominator and then cancel it out. So if we did that, if we turn this into 2 times 3 minus x and turn the bottom here into 2 times y minus 2, now we can cancel the 2 and our answer is actually dy dx is equal to 3 minus x over y minus 2. And that is our rate of change. And you may not notice this, but if you're like a super mathy person, this is actually the equation of a circle that has a center at 3 and, where is it? It has a center at 3, 2, and it has a radius of 2. Okay? Now the radius actually doesn't really matter that much because the rate of change will still be the same no matter what. But it does have to, the numbers do actually have to be plugged into here correctly. So there we go. There's another implicit differentiation example. We're going to do one more, and I think that you're going to feel pretty good about this. All right, here's an example. And these are the kinds that I actually like more than anything else. They're pretty simple. They go pretty quick. They give you the chance to practice your derivative rules. You don't lose yourself in the algebra. But you should be able to do ones that are a little more challenging. If you want to be really good at implicit differentiation, you should try some that include the chain rule, include the product rule, maybe including the quotient rule. Usually we stop around the product rule, but nonetheless, I only really care that you know how to do basic implicit differentiation, but you can challenge yourself further. If I want to find dy dx in this case, dy dx, I'm going to follow my procedure. Apply the appropriate derivative rule to each term. If it's a y term, put a dy dx on it. Well, the derivative of this part right here is just going to be 28x to the 6th. It's an x term, so nothing special there. Here we have sine of y, and the derivative of sine is cosine, so I'm going to do cosine of y, and because it's a y term, I'm going to put a dy dx on it. Dy dx. Now here, you can technically skip steps 2 and 3. Actually, you can skip steps 2, 3, and 4, except that my steps tell you to put this on the left and this on the right. So if you want to do that, that's fine. So we'll subtract this from this side, and we'll get negative cosine of y, dy dx. So we put it on the left, so that's step 2. Step 3, move the terms that don't have a dy dx over to the right, so we're going to subtract 28x to the 6th, which doesn't really matter. We can get rid of these negative signs because we can multiply or divide by -1 on both sides, and these negative signs go away. But for now, we'll leave it because it's not a part of my procedure. But technically, you can do that. Now, step 4, factor out dy dx from the left side. Well, I don't really have to because there's no addition or subtraction over here. So it's actually already factored out. It's by itself, and I got this over here. But if you really want it to look like what we had before, we'll put it over on the left side. Dy dx times negative cosine of y is equal to negative 28x to the 6th. 8, there we go. And then step 5, divide both sides to cancel what's with the dy dx. Well, we got to cancel a negative cosine of x. So we're going to divide by cosine of y. Divide by negative cosine of y. Divide by negative cosine of y. And now you can see we have a negative divided by a negative, and a negative divided by a negative is a positive. So we can cancel the negative, and all we have left is dy dx is equal to 28x to the 6th over cosine of y. And that is our rate of change in this in this relation right here. Okay? Well, I think that's enough. If you have any questions, let me know. I encourage you to look up other videos on implicit differentiation or look up procedures on the internet on how to understand implicit differentiation. The more that you investigate this, the better you will be at it. And the better you are at this, the better you will be at calculus and at mathematics in general. Okay? Well, good luck, and I'll see you later.